All right, everybody, lecture 3. It would help if I went to lecture 3. Let's get started. I did another thing on the attendance where I want to see where everybody's at with their manual. I'm just curious. This next homework assignment is due on Wednesday, and it does require your manual. Now, if some of you are having issues with it still being in the mail or whatnot, I can sort of work with you on getting it turned in and whatnot. Basically, the purpose of this assignment is just to force you to open the manual a little bit and just look some stuff up. Again, it's a pretty easy assignment. How did homework 1.1 go? Like I said, it's short, so it's just really trying to get you used to the load combinations, trying to get you in that headspace. We are going to use those load combinations quite a bit this semester, although we're not going to use all of them. Really, I just want you to get in the headspace of thinking about nominal loads versus factored loads. So a lot of our problems are just going to be, here's a dead load, here's a live load. And so 1.2 dead plus 1.6 live is going to be our most commonly used load combination in here. Honestly, I might have a problem where you use a different one, but mostly not. Any questions? All right. Today what we're going to do is we're going to talk a little bit about the manual. So I noticed a number of you brought them. That's great. If you're still waiting for it in the mail and whatnot, it's not the end of the world. I just want to talk a little bit about it, how it's organized, what's in it, and so on and so forth. So let's talk a little bit about the steel manual. To begin, I'll mention a little bit about AISC. AISC is the American Institute of Steel Construction, and they are the basically the technical specifying body for steel construction in the United States, period. Okay. A lot of what they do and a lot of the research and technical specifications that they generate drive the production of other specifications and whatnot in the U.S. But basically, when it comes to steel construction, they are the authority. They do a lot of work with producing design guides, specifications, technical manuals. They have an engineering journal and whatnot that keeps everybody apprised with the latest trends in the research. But they're probably their most commonly known publication is this, the Steel Manual. I have heard students refer to it as the Steel Bible on occasion, given the pages and whatnot. I will just call it Steel Manual and whatnot. But if you just go to any random civil engineer's bookcase, there's a pretty good chance there's a steel manual on it. Maybe not this version, but there is a good chance you're going to find a steel manual. It's just a very, very handy resource. It's got a lot of good information for you all as civil engineers, even outside the realm of steel design and whatnot. It's just a really handy resource. This thing is scary, I think, the first time that you open it, because you look at it and you go, good gravy, all the stuff that's in here, because it is daunting. There's a lot of info in here. If you look at the side of your manual, you will see these sort of like black and gold inserts. Y'all see these? The one that says like GEN, beam, column, tension, so on and so forth. The manual is broken down into 17 parts, and each one of those parts can be found with one of those inserts. But I often kind of tell students that it's convenient to think of the manual in sort of 3 main chunks. Okay, so the first 2 parts are the dimensions and the material properties. So we're talking about like what is the flange width on a W10 by 49? What is the yield strength for A572 grade 50 steel, and so on and so forth. All those sort of seed key lookup values you're going to find in either parts 1 and 2. Okay, part 16, the tab that says SPEC, you can see that down here, the one that says spec. That is the specification. That's the and I'm going to talk a little bit about that here in a bit. But that's sort of the document that guides how we design structures in the United States. Everything in the middle are the design aids, and that's really what you're paying for. That's what the money's for when you proverbially write the check for the manual. You're paying for that stuff in the middle. Now, some of you astute observers would be like, well, you missed one. You missed Part 17. Part 17 is just like a general reference. It's got like SI stuff, unit conversions, math formulas, stuff like that. Still a nice little handy tool, but it's easily, I don't want to say looked over, but you know how it is these days with Google. You can find a lot of that stuff. Okay, I want to start opening the manual to get used to some things. So the first thing I want to do is I want to have everybody open their manuals to a table like this. So just so you are aware before we get to this, you're here, you made it. For the alarm, this is table 1-1. It's the dimensions of rolled shapes. This screenshot is going to look a little different because this is from the previous edition of the manual. So you might not find this exact, screen capture, but I want you to find like a W shape. I'll tell you what page that I'm on. I'm on page, let's go 1-18. Okay, 1-18. I will put this here so that you all can see this. So there's a couple things you're going to find that are a little different. I'll give everybody a chance to flip through in case you're here. One of the things that this actually changed from the last edition of the manual to this one, but if you look here on the screen, the table is all white, and then if you look at the in your manual in front of you, you will see that they have like white, gray, white, gray, white, gray, and they shaded every other line to make it easier to look up. I actually think that's a really valuable benefit because I know that during homeworks or exams, if you're needing to look up value, sometimes it's easy to look up a value on the wrong line. So doing that I thought was really, really nice. Now a little bit about the anatomy of this table. So what you're looking at on the left side of the left page and the right page all correspond to the same shapes. So for example, if you look at a W27 by 129 on the left page and you track that over to the right page, there's a corresponding row on the right page that says 129. Can everybody see that? Now, what's going on here is this is the best way of describing it. Everything that's on the left side, this is stuff that you can measure, like with an engineering scale or a ruler or a caliper or something. Everything that's on the right side is stuff that's like computed. So we're talking about things like a moment of inertia or a radius of gyration or a centroid or stuff like that. That's not always the case, but that's sort of a gut feeling, is that the stuff on the left side of the table is stuff that you can measure, and the stuff on the right side of the table are sort of section properties that you would compute. We will be using these tables a lot, like almost like every day for the rest of the semester. So I do want you to get somewhat familiar with them. There are a couple things that I want to point out. The first thing I want to point out is this right here on the top left. You can see this sort of schematic that's associated with the table. I would really want you to make sure that you're taking a look at this. So like for example, if I ask you for the flange width, okay? So here in a bit, if you're not sure what the flange or the web is, this is the flange. So if you ever have an I shape, the top and bottom is called a flange, the middle is called a web, okay? So if I ever ask you what the width of the flange is, and you're like, wait a minute, I don't know what term that is, you can look at that schematic and go, okay, the width of the flange is B sub F. So I can look in the table for B sub F. And so these symbols are going to correspond to what's in this schematic up here. So make sure that you're following along with that, okay? Now, the other thing that you might notice is that for some of these dimensions, there are two values. So for example, if you look at the depth, okay, there's two values. You have a decimal value, and then you have this fractional value, okay? That's very common. The difference between the two is what they're used for, okay? The fractional values are used for detailing. So detailing would be things like drafting or drawing. So if I asked you to draw up a shape in, say, AutoCAD, I would have you do that using the detailing dimension. But for the purposes of design, we're going to use the decimal dimensions, okay? I've been teaching this class for a very long time. I say this, and I'll say it again. I guarantee you there will still be somebody who doesn't do this. But whenever we're doing design calculations in this course, you use the decimal values, not the fractional values, okay? Because what they're doing here, so this, for example, this 27.6, what they're doing is they're rounding that to the nearest sort of increment that you would find on a ruler, and that's what you would put on drafting. So this is 27.6, but they're saying let's round that up to 27 and 5/8 and whatnot. So what that means is that if you were to use 27 and 5/8, you would be overestimating the depth and whatnot. So please make sure that you're using the decimal values, not the fractional ones. Okay, does that make sense? So we're gonna, I mentioned that we're gonna see that, and we're gonna be doing this quite a bit. So this is something I wanted to get right off the bat. Okay, the design aids, like I said, this is what you pay for. Okay, and you can find design aids really by just flipping through any central part of the manual and finding any table that's colored like this. Like you'll see them all over the place, and there's oodles and oodles of them. You'll know you're sort of in design aid land when you see the green and the blue, okay? And that's not to say that every design aid is colored that way. Like there's a couple that aren't, like coefficients for eccentrically loaded connections, lower bound moments of inertia, sometimes those are the same. But for the most part, you will find design aids that have sort of a green or blue tint to them. And the reason for the color differences is the change in design philosophies. Any number that's green is going to correspond to allowable stress design. Any number that's blue is going to correspond to LRFD. And any number that's black is going to not matter. Like, for example, this is a W24/62. This term ZX is a property of the shape of a W24/62. And that property doesn't change depending upon what design philosophy that you are in. But the capacity does, okay? We are going to be using the blue numbers, not the green ones, okay? So don't look up any green numbers. And again, I don't think there's really, like you'll find, like if you were to survey the structural steel design courses in the United States, you would find probably most folks are just teaching the LRFD approach. Some might be teaching both, but I don't really think you're going to find many that are still doing ASD. ASD is, like I said, it's sort of going out the wayside, I think, in the terms of structural steel design. Okay, any questions? Okay, now, the code and the commentary is the stuff that's in the back. It's the stuff that starts with SPEC, okay? And SPEC is going to look a little different than the rest of the manual. Unlike the manual that has like tables and charts and figures and things like that, if you turn to the SPEC section and start flipping through that, it's going to look like a specification. It's going to have codes, provisions, equations, things like that. The specification is the document by which we design structures in the United States. So for example, and it's organized by chapter. So I have here a section that's the chapter for members on compression. And again, bless you. Don't hold these page numbers to the bank, because again, this is a little bit of an older edition. I'm actually going to pull up the new specification here in a sec. But this is the chapter on compression. Okay. So one of the things I'll point out is that if you notice, if you look at the rim of the page, so if you're in the main body of the specification, the page border is white, but a little bit further back, the page border is gray. You all see that section with the gray page border? Okay? So what that means is there is both a code and a commentary. Okay? And the sections are one-to-one. So for example, Chapter E is the design of members for compression. So what type of members in buildings are we going to be designing? Like what types of elements are we going to talk about when we're designing members for compression? The columns, right? We're going to be designing columns with Chapter E. Okay, so the code, this is Section E1. And Section E1 tells us, how to compute the compressive strength and so on and so forth. It tells us what the resistance factors are. And then there is a commentary, an associated commentary for Section E1. So the idea is that the code will tell you what to do. And the commentary will tell you why you're doing it, okay? So if you're ever in practice and you're ever looking at an equation, like why is that equation formatted like that? Or why are we using this value? Why is 0.6 showing up? The commentary will most likely tell you why. The other thing the commentary is used for is whenever a manual changes from one edition to another, the commentary will tell you, hey, back in 2012, there was a building that failed, and we noticed connections were doing this. So we did some research, and we found a new limit that we needed to check, or something like that. And so the commentary will help give you a little bit of the history of why a provision is the way it is. So in practice, the commentary is a good map for why things are the way they are. And there is a one-to-one with that. For every section in the code, there is a section in the commentary. The Steel manual does it like this, like they list them in different sections of the manual. A lot of other provisions will do it side by side. So you'll open up like the bridge code, and you'll see the code and the commentary literally all on the same page. Everything on the left is the code, everything on the right is the commentary. I just mentioned that that's a very common trait of codes and specifications. I did want to mention, before we get to some properties on Steel, a couple of things that I uploaded to the Blackboard course shell. Okay, there is a section in the lecture notes and supplements called AISC Errata. I think probably you all have at least seen that link. The first thing I'll point out is this PDF that's the specification. So I uploaded the specification, which you can download on AISC's website for free. This is section 16 in the manual, all here. So, for example, we can go to Chapter E, the design of members for compression, and we can find all of those provisions that we were talking about. And then as you go through here, you can see, like, everything that you see here is what you could find in the manual. That part you can download for free, okay? So all of those provisions that are in the manual in the specification section are right here. So it's a nice little handy electronic reference. The other thing that I posted was this Excel sheet, okay? If you download this Excel sheet, what you'll see are two tabs. The first tab is the README. I'm not saying you can ignore it, but this README, what it'll do is it literally describes what every column is in the adjacent sheet. So what is column Q? Column Q is the thickness of the web. Column R is the detailing value of the thickness of the web, and so on and so forth. And column Q and column R. Go to the database, and then you see this massive Excel sheet. What this is every one of those dimensions and details all in one sheet, right? So we can go, like for example, if we go to the, right here, we were looking at a W27 by 129. We can go through here. Here's a W27 by 129. And what do we see? We see the area is 37.8. The depth is 27.6. The detailing depth is 27 5/8. And that's everything that we see here. Here's the area, here's the depth, the detailing depth, and so on and so forth. So if you want a little Excel reference for all of those dimensions and details, you can download that right now, okay? So, and that is actually kind of handy. I mean, how many of y'all remember that analysis project we did last semester? You think I sat there and just typed out all those numbers? Like, no, I just did this and snipped out the W12s for that truss that we designed from this building to the biotech building last semester. Okay, let's go back to this. All right, any questions? Okay, I'm not going to pull this video up. I'll let you look at this at your own leisure, but you're engineers. I have to believe that everyone in here has at least seen one episode of How It's Made. Has anybody ever? Okay, good. Like, it's like, I think that's something that's like common among engineers, that like, you know, it's like we gravitate towards this show on the Discovery Channel for some reason, where it's like, ooh, I'm gonna, you know, spend 3 hours learning how bubblegum is made or whatnot. So tell me you haven't been like sick at home doing that, like everybody has. Okay, I found the clip on how steel is made. I'll let you watch that at your leisure, but there is sort of one thing I will mention that I think is kind of salient to structural steel in the United States, and that is that we are not really producing new steel as much as we are recycling old steel, at least in the construction market, okay? So typically what we're doing in the construction market is we will take scrap, melt it down, adjust the chemistry to make sure it meets this, the material spec, and then just roll it again, okay? And that is how we're producing most structural steel in the United States. And I keep saying structural steel or construction steel because I'm separating that from automotive steel or whatnot. That you know, could be produced differently. But really about 90% of the construction steel that we produce nowadays in the United States is recycled, okay? You'll see there's a new trend in structural steel making that you'll see the cropping up what are called mini mills. They call them mini mills, but these things aren't mini. They're like, you know, these huge facilities. They're like a mile long. But what will happen is the facility will be located next to like a rail car or a railroad, and then the rail car will come in with a bunch of scrap. They take the scrap, they stick it in a big furnace, they melt the steel, they collect a sample, check the chemistry. Chemistry is probably going to be a little off just because it's scrap, so they throw in a little vanadium or a little bit of nickel or whatever they need to throw in to adjust the chemistry, and then start rolling it. So it's a pretty straightforward process. This video, it's about 5 minutes long, goes through the process. It's worth a look. Okay. I have to believe in the land of mechanics of deformable bodies or civil engineering materials or what have you. You've seen one of these before, am I right? Everybody has seen a stress strain curve before? Okay. If not, or it's been a long time, let's just make sure we're on the same page. So a stress strain curve happens when you take a sample of steel, you yank on it, right? You yank on it until you snap the thing, right? And I'm being very loose in my language there, but really, you know, you're doing that at a controlled rate under ASTM standards, and you collect load and deflection data, and then you take that load and deflection data, you take the load, you convert it to stress, you take the deflections, you convert it to strain, so that you're removing the individual dimensions of that one piece so you can get some qualities about just the material. And you get a stress strain curve that looks like this, okay? Everybody seen this before? Okay. So just to recap a little bit about the mechanics of how steel behaves, steel has, for a simple discretization, and again, I think there's metallurgists out there who would cringe at me saying this, but steel, like at least from an engineering perspective, we sort of consider it having two sort of distinct ranges of behavior. One is elastic, and one is inelastic. So elastic behavior happens in this part right here. So elastic behavior, what happens is you take a piece of steel, you put some load on it, you'll take that load off, and then the steel snaps back to its original condition, where the steel behaves very much like a rubber band. You take the rubber band, you stretch it, you let it go, it snaps back to its original shape, right? That's how a rubber band behaves. Materials like steel have that behavior as well, and we call that elastic behavior, okay? Now, we can characterize this behavior with really two properties. The first is, when does elastic behavior stop? And for all rights and purposes, we'll say that elastic behavior stops whenever the material starts to yield. So yielding is when those material deformations start to become permanent, okay? Sort of like and just to keep it very simple, it's like when the material stops behaving like a rubber band and starts behaving a little bit like taffy, and you yank it and let it go, it has a permanent elongation to it. And that happens at around the yield stress, okay? The other number that we can use to characterize this is the slope of this line, okay? The slope of that line, what do we call that? Do I remember this from Mechanics of Materials? Young's modulus, right? Young's modulus is the slope of this line. And the slope of this line is 29,000 KSI or 29 million PSI. And again, just to make sure that we're clear, I am not saying that steel can hold up 29 million pounds per square inch. That's not what I'm saying. I'm saying that the ratio of the applied stress to the resulting strain, the slope of that line, is 29 million pounds per square inch or 29,000 kips per square inch, okay? That 29,000 is a number that you can set your watch by, okay? The Young's modulus of steel, it's one of those numbers that as an engineering student, I believe should just be burned into the back of your head before you graduate with an engineering degree. It's like the unit weight of water being 62.4 pounds per cubic foot. You just sort of should just know that. Well, the Young's modulus of steel being 29,000 KSI is a number that you should just know, okay? So I am going to check you on that a little bit. The unit weight of steel, I think I mentioned this last time, that if you have a cube of steel that is 1 foot by 1 foot by 1 foot, that a solid cube of steel, it would weigh 490 pounds. That is also a number that you can set your watch by. Admittedly, we don't use this number as much in building design, and you're going to see why in a very short bit. The other thing that I would like to mention about steel is sort of the scale of this, this stress strain curve. So remember, this is elastic behavior. You have this range right here where the steel will freely deform under constant load until the structure of the steel, the crystalline structure realigns, and it can start accepting load a little bit until it gets to the point where the sample wants to fracture. If this were a big old football field, okay, and this is the end zone, and this is the end zone right here. From here to here, from here to this yield stress, that's about the 1 yard line, okay? And then from here to here, that's about the 10 yard line, okay? And then from here to here's the rest. Steel has an incredibly remarkable quality in that it can withstand deformations well beyond yielding, okay? It is very strong in its ability to do that. It behaves much better in that regard than, say, concrete. Concrete doesn't really work that way. Concrete is a very brittle material, right? I mean, how many of you have seen cylinder tests, right? You take a cylinder, you push it cracks, right? Steel doesn't really do that. Steel has an ability to stretch and withstand those inelastic deformations. If concrete is a brittle material, steel is a ductile material. So if you ever hear me use the term ductility, like what is my scientific definition for ductility? Ductility is the ability of a material to withstand inelastic deformations. And steel is a very ductile material. So I just want to put this in scale. Now, and the reason why I think that's so relevant is because a lot of what we try and do in steel design, we try and a lot of times limit stresses here. We try and keep the behavior there. That's not to say we don't do that all the time, like in certain connection and tension member situations we allow up to fracture. But like in beam deflections, we try and keep those deflections elastic as much as possible. So, okay, any questions? Now, the Young's modulus and the unit weight, they change from, they don't change. The Young's modulus and the unit weight are the same for just about any grade of steel that you can look up. What does change, like when you look up different grades of steel, what does change from grade to grade is the stress at which it yields and the stress at which, or its maximum ultimate tensile stress. Those are the two values that change, okay? Now, where do you find these values? You look them up, okay? So I want everybody to turn to this. This is table 2-4. I want to turn to this one. Table 2-4 on page 2-56. Now, again, I put a forewarning here. This looks different than what's in the manual. As I mentioned, the manual has not been made digital yet. They just released it. So I haven't screenshotted the new table yet. So table 2-4 on page 2-56. And while you all are turning to these, have you noticed that the manual is very, very big? And notice that there's a lot of pages. And if you have to keep turning to this page, it might be tough during a homework or an exam. This is my manual from last year. See these little tabs? So, for example, this table, here it is, right there, okay? So I have a series of tabs in my manual to be able to find some of these references very, very quickly. And I've even started doing that on my new manual over here. I haven't finished yet, but I do strongly recommend that you include some tabs in your manual for some of the key tables that you're going to be looking up quite a bit. As an example, table 2-4, I would put a tab in your manual. You're going to be using that quite a bit, okay? That's one that I would tab. And then as we get closer to exams and homeworks, like as we start getting into the thick of things, there are, like, for example, shear lag, I'll say, okay, you want to tab this table. this section, you might want to tab this table. During the exams, you're going to have both the manual and a formula sheet. So some stuff in the manual you should tab. Some stuff you can just write down on your formula sheet. We'll clarify that as we get closer to those topics. Okay. So what you can do is if I give you a problem that's, for example, let's say I give you a problem and I say, just based off of what's here on the screen, I want to do a problem and the steel is going to be A500 grade, A501 grade A. Let's just do, or A501 grade A or A501 grade B. So like A501 grade B, the yield stress is 50 KSI and the ultimate tensile stress is 70 KSI, okay? So 50,000 PSI or 70,000 PSI, okay? So if I tell you the grade of steel, you can look up the yield stress and the ultimate tensile stress very easily in table 2.4. Now where things get a little funky is grade A36, okay? So the yield stress is 36 KSI. But for the tensile stress, we have a range. So that's a question. If you're an engineer and I give you a range of the ultimate tensile stress from 58 to 80, what should you use? The smallest value. That's 100% right. That is absolutely correct, okay? Because if you are the engineer and you're designing this member and you choose a larger value, that might result in a smaller design. The most conservative option is to choose the value that's going to result in the safest design, in which case you choose the smallest, okay? That is 100% correct, which leads to a very reasonable question. Well, Dr. Mike, if we're always supposed to choose the smallest, why the heck did they put the range there, right? It's a reasonable question, right? So I'll tell you actually where the range comes from, and it actually comes from ductility, okay? So the thing about material behavior is that if you start increasing its strength, you have a tendency to decrease its ductility, okay? So back in 1994, there was a major earthquake, the Northridge earthquake. You can look it up. At the time before the earthquake, we were telling, and I say we, I mean the steel industry, was telling engineers that you needed to detail structures a certain way and that moment frames were really the best way of detailing structures in seismic zones. Without getting too far into the weeds, a moment frame resists lateral loads by using these really beefy connections. And so moment frames allow a lot more sway, but the perception was that they allowed a lot more ductility. And so what was happening was the engineers were assuming a certain amount of ductility, and they detailed all these structures in the 80s and 70s and whatnot, assuming this behavior. And then this earthquake happens in 1994, and they start looking at all these steel structures that were supposed to survive all these earthquakes, and they weren't. They were fracturing at loads that they probably shouldn't have. And when they started doing material tests, they found that the ultimate tensile strength was way higher than what they had thought it was going to be. So they put this range here to indicate that you might have some higher tensile stresses that you would expect, so you need to pay attention to that from a ductility standpoint. For most, routine design won't really have an effect, but for earthquake engineering, it might. So that's why. That's why that's there. Now, you are using the 16th edition, this is the 15th edition, and this is the screenshot from the 15th edition. Yours looks different, okay? One of the things that is very different from manual to manual is this table. And what changed from the last manual to this one is that the standard yield stress for a lot of shapes changed. This actually was kind of a big change from the last manual to this one. So for example, in here, unless otherwise noted, the default yield stress for angles was 36 KSI. Now it's 50, okay? And that is a big change, okay? And basically the reason is that if you take a piece of angle and go test it in a tensile machine, you'll find that its yield stress and tensile stress were well above these values anyways. It just took a while for standards and whatnot to certify them as exhibiting those loads. So that's really kind of a new change in the last manual. Last thing I want to mention before I move on to the next slide, if you look at my slides, you'll see that my text here is in green. Anytime I have green text on my slides, my intention is that references page numbers in the manual, okay? So if you see green text, that's my a manual reference, okay? Sound good? All right. Okay, I've been mentioning a lot of angles and channels and plates and all that stuff. Let's talk about the products that we build structures out of. And so really the two types of products that we use are plates and bars. And so we can take plates and fabricate members and components out of them, or we can use rolled shapes that come right from the mill. So rolled shapes would be things like a channel or an angle or what have you. Now, some of you are probably thinking, well, Dr. Mike, don't you call them I-beams? We don't really use the term I-beam anymore, because there are a number of different classifications of I-beams. For example, we have a name of I-beams called HP shapes. So if you look in the manual, you'll find W shapes, M shapes, S shapes, HP shapes. So HP shapes are the ones that are typically used for piles and foundations. The most common quote-unquote I shape that we use in steel design these days is called a W shape. And the term W stands for the fact that the flanges are a little bit wider than they are in a standard shape. So if you hear me use the term a W shape, or hear me use the term wide flange, that's what I'm talking about. I'm talking about this I-shaped cross-section that like you're thinking, isn't it an I-beam? No, it's a wide flange shape. So I probably will very sparingly use the term I-beam throughout the semester, even though some of you are probably thinking, isn't that what they are? No, there is a difference between the two. Your I-beam, you're probably thinking of this, whereas the W-shape, the flanges are a little wider. Okay, like I said, if you're looking at this type of cross-section, the top and bottom pieces are called the flange, and the central component is called the web, okay? That's just some terminology that I think you need to be aware of, but we're actually going to pay attention to some of those specific components later. Like as an example, when you're looking at W shapes or any type of I-shaped cross-section and you are looking at its capacity, its shear capacity is largely governed by what's going on in the web, okay? So, for example, when we look at the nominal shear capacity of a W section, it's going to be 0.6 times the yield stress times the area of the web, just the depth times the thickness. So I just mentioned that because you'll see that a little later. Angles, we use legs to express this. So you might have equal legs, or you might have a long leg and a short leg. So I just throw that out there for terminology. Anytime you're dealing with a rolled shape like a W section, the top flange and the bottom flange are going to be the same. That isn't always the case on sections like plate girders. Like if you go out to some longer span highway bridges, so how many of you have seen the plate girder on the interstate bridge there at Nitro? That huge ridge. Guarantee you the top flange and the bottom flange of those I sections are different. They are not the same size, okay? So it would be a singly symmetric cross-section. In other words, it's symmetric this way, but not this way. Whereas a W shape is doubly symmetric. It's symmetric this way and that way. Does that make sense? So rolled shapes are going to be like that, okay? I just throw that out there just for specification. Okay, the last thing I'll mention is a note on naming. So if a little bit earlier I said that we don't as often use 490 pounds per cubic foot. The reason is because of how we name a W section. Okay, so I want to consider a W27 by 129. Okay. A W27 by 129 is unique. There's only one W27 by 129 shape in the manual. So what does that mean? The W corresponds to the type of shape. So it could be a W, an M, an S, an HP, a channel, WT, whatever. So that's just the family of cross sections that we're looking at. So we have a W section. What does the 27 stand for? The 27 stands for about how deep it is. And I say about because if you look at all of the W27s, there's going to be variations in its depth. Like the W27 by 129 isn't 27 inches deep, it's like 27.6. It is sort of corresponds to how the sections are rolled. So some of them might be a little deeper than 27 inches, some of them might be a little shallower than 27 inches. But all of the W27s are going to hover at around 27 inches. Okay? So that's the W, the 27. What about the 129? The 129 refers to how heavy the beam is. Okay? So a W27 by 129 is a W shape that's about 27 inches deep that weighs 129 pounds per foot. So every foot of that shape, pick it up, put it on a scale, it's going to weigh 129 pounds. So this is a number that you're really going to want to key into when we start doing design, because there's going to be problems where I say, here's a tension member, select me the lightest W14 section you can find. And so what you're going to do is find the W14 with the smallest second number that safely resists the loads, because that second number tells you how heavy it is. Now why does that matter? Why would I choose a W27 by 129 over a W27 by 539? Like, if the W27 by 129 works, the W27 by 539 certainly works. So why would I pick this one over the 539? Cheaper. It's cheaper, right? We buy steel by the pound. So we want to pick the section that is as light as possible, because that is the least hit on our wallet. Okay? Does that make sense? Now, angles are a little different. Angles are named, so if you have an L shape, you can either have an equal leg angle or a unequal leg angle. So this is an unequal one. So we have a 6 by 4 by half. The 6 and the 4 correspond to the depth, or the depth of one leg and the depth of the other, and the half is the thickness of the leg. You always put the biggest number first. You don't do an L4 by 6. It's always L6 by 4 or L6 by 6 or L8 by 6 or what have you. It's always the biggest number first. Okay, so this is how these sections are named in the manual. I just mentioned that because this is the type of stuff that we're going to just sort of assume, oh, you all know what I mean when we start getting later on in the class. All right, any questions? Okay, I do want to pull something up just to sort of make the point. So I've got another homework assignment that is due Wednesday, and I'm just going to show you what it looks like. The purpose of it is to just get you familiar with the manual. So I'm giving you 10 questions, and it's basically just like, using the manual, respond to these questions, okay? So what is the flange width of a W30 by 261? So you're going to open the manual, look up W30 by 261. It's a 10-question quiz on Blackboard. You input that number, move on, right? What is the radius of gyration of this? What's the warping constant for this? And so basically it's just open the manual, look some values up. Some of the stuff is in the tables in the beginning. Some of it comes from the specification. Again, I don't think this homework will take you more than 15 minutes. I really don't. It's not intended to be a heavy homework. It's just meant to make sure that you get familiar with the manual. I want you to get comfortable with the book, because we are going to use it quite a bit, so I want you to get familiar with it. Any questions? And again, if it gets to the point where it's like Tuesday or whatnot, you still don't have your manual, let me know, okay? But you do kind of need to get it ordered if you haven't already done so. I mean, like, you should have already done that, but I mean, starting when we come back on Wednesday, we're going to use that manual. We're going to use it a lot, so I don't want you to get held back. A couple of the initial homework assignments, I put some dimensions on the homework assignment to like facilitate if some of you are having mail issues. I've been teaching this class for a while, and every now and then I have a couple students that, they're literally showing me their receipt, and it got lost in the mail. So I'm sensitive to that. That's not your fault. But if you haven't ordered it, order it. Sound good? All right, I'm going to pull up the code one more time in case anybody missed it. You all have a wonderful weekend, and I will see you on Wednesday.